Hands is a new programming system for children that we designed to be easy to learn and use. Unlike the designs of most programming systems, our process for designing Hands placed a primary emphasis on usability. The system addresses many of the problems that are experienced by beginner programmers, which have been identified by researchers over the past 3 decades. In addition, we have conducted new studies to examine how children and adults solve problems before they have learned to program. By matching these natural tendencies, Hands reduces the distance between a programmer's ideas and the implementation of those ideas in program code. Hands features a new model of computation that enables people to think about their programs in familiar, concrete terms. The program is organized as a series of event handlers, because this style most closely matches the solutions people wrote in our studies. The system provides queries and aggregate operations, enabling many common actions to be expressed simply and naturally. And the system provides high-level support for creating the kinds of interactive graphical programs children are mainly interested in. One of the big challenges for beginners is to gain an accurate understanding of how computation takes place. Traditionally, programmers have to learn a completely new model with complex rules about the flow of control and accessibility of data. In contrast, Hands uses the familiar model of a character sitting at a table, manipulating cards. The character's name is Handy. In Hands, all information is stored on these cards. Each card has an unlimited set of properties, or name-value pairs. Cards make all of the program's data visible to the programmer, even when the program is not running. Cards can be flipped face down to show the back. This card has a generic back. But if the user puts a picture into the back property, the picture is displayed when the card is face down. The white area in the center of the table is the board. When cards are off the board, they are displayed as little windows, but when they are on the board, they are displayed without the window. This makes it very easy to create characters and scenes. It is easy to display strings or numbers on the board, simply by placing them into the back property of a card, either by direct manipulation or by the running program. Hands has built-in support for animating objects. If a card has a speed and a direction property, Handy will automatically move the object according to these values. The programmer gives Handy additional capabilities by adding code to Handy's thought bubble. This is done by creating a set of event handlers. Each one specifies an event Handy should watch for, such as collisions between objects, keystrokes, or mouse clicks. Inside an event handler, the programmer specifies what Handy should do in response to the event. When the program is running and one of these events occurs, Handy executes the code in the matching event handler, then looks for the next event. The event-based approach and the verbose style of the language match the way non-programmers wrote problem solutions in our studies. Context-sensitive menus assist in constructing a correct program. This new event handler will be triggered when the bee collides into the flower. When this happens, Handy will stop the bee. Clicking the play button runs the program. Handy's picture begins animating to indicate that he is working, even if nothing visible is happening on the screen. The system also provides a test window, so the programmer can test code without waiting for an event to trigger it. This statement sets the nectar property to 0 on the card name Buzzy. When the Test It Now button is clicked, the change is immediately visible on the card. Hands provides a way for the programmer to find all of the cards in the system that match certain criteria. Queries return a list of all matching objects. In this example, all bees returns all of the cards that have the string B in any slot. All operations that work on single cards will also work on lists of cards, including the lists that are returned by queries. This expression returns a list of the nectar properties of all the bees. 'And this command moves all of the bees down by 10 pixels. The combination of queries and aggregate operations, along with the list operators that hands provides, make it convenient and natural to express many common operations. For example, this simple expression calculates the sum of the nectar of all of the bees. To accomplish this same task in a traditional programming language, such as C or Java, would require a pre-planned data structure containing all of the bees, as well as temporary variables, iteration, 3 kinds of parentheses, and other punctuation. All of these things are known to cause difficulties and errors. In a user study with 5th grade children, hands was compared to a version of the system that lacked 3 important features: queries, aggregate operations, and the high visibility of data. In this comparison system, the children had to use more traditional programming techniques to solve their tasks. The children who used hands performed significantly better than the children who used the comparison system. Hands has been used to implement a broad range of games and simulations. One high school student compared hands with a commercial programming system for children called Stagecast. He built Pac-Man in each system and concluded that hands was easier to use, required fewer lines of code, and enabled him to implement more features. The success of hands can be credited to the human-centered design process we used. The new model of computation and the unique set of features in hands would not have emerged if we had simply relied on technical criteria, prior language designs, or our own intuitions. The designers of future programming systems can benefit from the knowledge we collected and the process we used.